Thanks. Thanks also for saving me a few time, 15 minutes or kind of that. So I'll be happy to have more time. So I will talk about the next leading order in general. I put the quantum correction, so it's more general. Any RQCD alpha S or alpha or whatever. All the technology should be similar. So my plan, because I have 3 lectures, so the first one I just give you very basic stuffs to introduce the basic notions of what kind of NL calculations you need to be care of, what is singularity. Actually, some notions have been mentioned before in previous lectures. So, like what is singularity, why there's UV singularities, the inferred singularities, what is soft singularity, collinear singularity. So I just give example, then you will understand it probably better. And this example very simple, but it's a real example, it's not a toy example. And then the second lecture, probably I will use a bit of time in the lecture 1, because it's the most dense of the lecture material you will have. It's to talking about the generics of the NO calculations, or using the modern technologies. And then the third lecture, tomorrow morning, I will talk something about more advanced topics, okay, like electric and BSM. So let's starting from something basic. So I give a very short introduction because I thought that many people have, many previous lectures gave the motivations why we need to go to the NA or even go to higher NA or N3A or whatever. So very sensitive. Huh? So the main point, of course, these diagrams, precision, right? So NA you gain precision compared to leading order. Leading order too crude. Of course, not only precision, but precision is one of the main points why you go to the higher orders. So the reason is because of your data, and the data has huge samples, and all these allow you to have a very precise measurement, and all these precise measurements, you need a corresponding precise theory to keep path of the experiment data, right? So it's very, okay. So in order to fully explore this HC data, you will see that several magnitude order magnitude measurements with different final states, and some even extremely precise, even at per mille level. So of course, we need to see something. If the BSM, for example, is a 1% level, we must care 1% of theoretical precision, right? If BSM is a factor of 2 of your standard model, of course, you don't care that much at the moment, right? So it's really, of course, the question of the precision, and it's especially in the first rounds of the HC, we don't see any clear evidence of the BSM. It's at least not BSM signals not easily be found. So the most of the interested would go into the precision phase, right? With your indirect searches and indirect search, yes, BSM. So we have seen this, no, not this plot, but we have similar plots to see the massive formulas at HC is, we know that the PP gliders and how we calculate a cross-section, or this is PP glider, but also similar as Viz as well, right? So how we calculate the cross-section is convoluted two of the Parton distributive functions with Partonic cross-section, and this is a very good approximations. We proved it for the colorless final state, and this is the only correction is power corrections. So this formula is not exact because you ignore all the power corrections. And these power corrections, of course, if you go to higher scales, its power corrections drops extremely fast. So you don't care about the high twist, these power correction terms, high twist terms. But there's more and more interesting, of course, in the fields that to looking at these high twist terms. But we will focus on the reading twist formalism, so because it's mainly mainly to go to the high energies. And typically, the things that's been introduced is pattern distribution functions as universal one, but it depends on some scales via the QCD evolution equations. Perturbative QCD literally gives you how this given scale at x value, you know all the scales, remaining scales. Of course, not go to non-perturbative regions, but up, for example, right? Perturbative region, you know all the scales, what is PDF it is. And there's a short distance part is mainly interested in probably new physics or whatever, comes into, and it is you can use in the perturbation theorem. And there are some couplings comes into some scales, like factorization scales and normalization scales where it comes into. And they are actually in principle, but this is can be improved, systematically improved if you include more orders. If you go to infinite orders, of course, this depends on 0. Right? So there's so this one, perturbation theory works is described a phantom universe. Huh? So if you, especially for these Platonic cross sections, you can go from the leading order. You can systematically improve the more orders, and these more orders, leading order, next to leading, or next to leading, include more orders. This will be reduce your remaining scale uncertainty, one of the main concerns in the perturbation calculations. These are scale uncertainties. And this scale uncertainty is very important is that if you calculate to NKLO, the scale dependence must be at next order. So that means NK plus 1 NLO. But if you go to O orders, of course, 0. So it's very important that why you go to high orders, you reduce your systematically theoretical uncertainties, right? So this is a big review, overview. I think Fabio has flashed his slides, a similar slide. But I will give to show you that actually 15 years ago at the previous HC, there are very little of a different calculation, because if you go to the more lakes, complexity, number of the external particles or more loops, so there's abilities you can go is quite low. So next to leading on the alpha is 2 loops. You see that 15 years ago, it's in only 2-to-1 process, like Higgs production or Julian, Z production, right? And next to leading order is almost by hand, so you can go already, go to 3, but beyond is very difficult. And even leading order, it seems not a problem, but if you go to high orders, of course, more complicated, both in the matrix element calculations and the phase-space integrations. And I think Olivier has said something about this. It's not trivial. There are different levels, of course, predictions. Even you have calculated something, but the calculation could be at a different level. The fully inclusive means usually you integrating all of the final states, right? Massless final states, so it's only total cross-section, not allow you to give the differential distributions. And the pattern level, that means you allow to have differential distributions, but not at particle level, not allowing to have the hydronizations or this kind of thing, right? And the fully exclusive, of course, means you have mentioned the pattern shell will have the hydronizations, so everything's particle level. And this fully exclusive automatic, so means these are in the older school fashion is do one process by hands. And right now, of course, merged, up to next to leading order, you can do. You don't need to by hands, just with computers, right? Electric computer with a few buttons. So it's this is things. So explain the notions what I mean. So the previously you see that even for 2-to-1 process Higgs production, it's only fully inclusive. There's no differential distributions 15 years ago, and next to leading order only pattern level. There's no fully exclusive predictions, and leading order, of course, you have fully exclude predictions. But it sees that it's very restricted. But now, of course, mainly motivated, triggered by the HC. There are many people working on the go to the more high multiplicity final state and go to higher loops, right? And even many strong loops in India, I think, to go into this phase. And so all these things are very technical, very challenging, of course. But right now, at least, I mean, you see that many, even in the 2 to 3 level, most of them is automatic, fully automatic, even go to 2 to 8 process at leading order, 3 level, and in one loop, typically you can go to 2 to 4. So that's, I mean, that's motivated by HC program and also the huge progress in the technologies. Of course, you can go further. I mean, it's not only talking about that. Previously, talking about alpha is because alpha is the dominant corrections at the HC. It's PP collider. But you can also look at other corrections like electromagnetic or electroweak in general, electroweak corrections, right? Do the same thing, and you will see what's the status on this, and it affects. Oops. Okay, yeah. So in fact, why I think 2 to 1. I think you should put also the automatic as well. Oh yeah, it's fully exclusive. So here is I put the pattern level, so it's not matching to pattern shower. If you have the both electroweak and QC correction, it's not trivial. So most of the it's not. I mean, here I changed its pattern level. It's not fully exclusive. So fully exclusive, only a few examples, simple examples. Then, of course, you can not only the standard model, you can go to beyond standard model and do the same things, all the different ideas, and you have different accuracies. So you'll see that this we can go in general way. So I will give third lectures to talk a bit on these and electroweak directions. So I give 2 quick examples. Is go to the highest accuracy as HC is in 3L or Higgs or di-Higgs production. So Higgs and ground fusion of Higgs production is achieved in 2015, and you see that I mean it's a big achievement in the PQCD calculations, and you see that the complex is completely different. If you go to from NNL, the diagrams is I think it's 100 times more, and integrals is also several orders larger, and also some mass integrals, all this kind of thing. And they develop different technologies. Reverse unitarity, differential equations, mailing binds liberalization, Hopf algebra of generalized. I mean, mathematics. Some mathematics even comes in too. So some modern mathematics comes in too. So all this helps you to have these big achievements. I would show this plot because first, of course, I do this, but secondly, because I would like to show you that the ratio as well. Okay, the previous plots do not show the ratio. So the ratio is, I mean, this is all the different cross-section divided by N3L cross-section. You see that the blue one compared to neck-to-neck-to leading order, the uncertainty, this is mainly scale uncertainty I mentioned, is indeed reduced very significantly, right, from each order. And the important point is leading order scale uncertainty is, in fact, is not correct, because the leading order scale dependence is too trivial. So the only more or less reliable scale uncertainty estimation or theoretical uncertainty according to the perturbation truncation is next to leading order. Okay. So then another example is you go to the not to this direction more loops, but go to the more legs, right? So jet multiplicity at next to leading order, highest jet multiplicity. So one is W plus jets. It's very important and dominant background for many searches or even for standard model measurements, like a TT bar measurements background. There are, I mean, in 2013, there are several, there are groups by Sharpa and Black Hat. They actually calculate W plus N jets, N equals 0 to 5 jets. I think it's their most proud calculations and put it on the Slack web page, I think. So these diagrams. So you see that this kind of thing is, of course, it's also very complicated. And there's many technology improvements like the unitary cuts and integrand reduction, Lagrangian relations, and inference subtraction. All these kind of things helps you to achieve, able to calculate this kind of diagram, 3D diagram, right? And of course, right now, some things automatically even, the previous inclusive level, I say that it's pattern level, okay? Pattern level differential distributions are not allowed to match into pattern shower right now, also allowed to match into pattern shower even automatically. But of course, the low mass precision is low. And this is you can achieve it by math graphs, and you will see that actually this is few comments, and it goes from this is neck to leading merging. You already tried the leading merging yesterday, but this is neck to leading merging, and with one jet, 0 jet, 1 jet, 2 jet, and next to leading merging, you see that actually data indeed favors, of course, favors. I don't see the rate is inclusive, the pattern level, right? So the green is exclusive, so matching to the pattern shower, you see that data favors right? So of course the inclusive one it's not sufficient. Oops. So right now, this is automatically. So I think you will see again at some point, tomorrow morning maybe. These structures in the math graph, 5MSO, and there are some technical improvement. So some next to leading order calculations, techniques is measured, but with modern techniques, you are allowed to go high mass precipitation, and also the method to general matching to match elements to pattern shower and merging of all are developed. So, okay. So I say all this kind of thing. Of course, Mr. Feynman too asked, right? We don't blah 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 blah. Just shut up and calculation. So I gave one example to calculate something and introduce a basic notions. This is I think I can imagine most simplest realistic example is z decay to QQ bar, and it literally can be performed by hands. Okay. The QCD corrections. So let us calculate these. So let us calculate next to leading QCD correction to Z to QQ bar decay. How do you do this? Of course, first you need the leading order, the bone amplitude. So draw your Feynman diagrams according to Feynman laws. I think this I don't need to introduce it anymore, right? Because it should be in the quantity field theory textbook. So writing down your amplitude. And this is your vertex, electroweak vertex, and writing amplitude. And for simplicity, assuming quarks are massless. I don't want to bother with this. Then squaring amplitude, just taking a squaring, and summing over the colors of the final state, and spins of final state, initial state, and averaging spin of the initial state. And this is what I get at amplitude squared level, right? So remember that alpha is defined E squared over 4 pi. Alpha is GS squared over 4 pi. This is just, enters into amplitude, but an amplitude square level it's written in the alpha and alpha S. And then do the phase space integration. So my phase space integration, two-body, right? It's very simple. Two-body phase space integration. And this is an exercise you can derive that. In fact, there's no leftover any. You don't need to integrate anything. So it's delta functions. So then you just quickly get these the leading order or bone level decay width. Then next to leading order, of course, I need the one loop, the amplitude. So I draw my one loop amplitude diagrams, Feynman diagrams. I write down my one loop amplitude, and then what I need to do, I need to worry only thing is right now I have the integrals. Okay, I have integrals. I write directly in the D dimension because I know that these integrals are divergent if you directly evaluate at D equal 4. So what I need to calculate of these integrals is two tensor integrals, right? So I put the Lorentz structure explicitly. So this is I1 and I2, two Lorentz. So you have the 2 and 1, right? Or this 1 times this, it gives 1, right? So I need to calculate these two tensor integrals. So these two tensor integrals, actually, I can write split into the Lorentz structure because of Lorentz invariance. No, not Lorentz structure, right? The only Lorentz stuff enters into my vectors into my integrals are p, q, and pz, right? So I can write it decompose it into pq and bz, and this one is a bit more the two Lorentz structure because you have also matrix that always enters into. So I can always write in this way, and they're symmetric, right? So I don't decompose it to b1, 2, and b2, 1. So I just write it this way. And then I want to solving this equation, solving this coefficient b1, b2, for example, right? How do I solving these? I just multiply my external, these Lorentz vectors pq and pz to your integrals, right? So I multiply these to be a Lorentz scalar in the left hand and the right hand as well, right? So of course I use in the unshared pq squared equals 0 because I take massless. So I only keep the p2, okay? And then to bz times I1 similarly, but right now I need to keep 2, right? So solving this coefficient, so then b2 is just my pq times I1 times pq times pz, right? And b1 is something just a solving. It's just linear equations, right? Is it working? Yeah, it's here. So then the question is, what is my PQ times I1 and PZ times I1, right? I just give an example that PQ times I1, you can come back to your definition of I1, then you did multiply PQ times IL, and then you can do the decompositions and further decompositions into some new denominators, right? L for PQ times L is L bar squared minus L bar minus PQ squared, or half, right? So then you can cancel the numerator denominator by one propagators, right? So then you can come back to the two integrals, but less number of the propagator integrals, the bubbles, right? 2-point functions. Here's 3-point functions. Then you go. Also, the numerator is 1, right? It's not the tensor anymore. So then what you need to do is you need to calculate these basis functions, right? Basic functions. So these basic functions, how can I calculate these basic functions? I think it's being also say something in the quantum field theory textbook probably, but I still introduce a bit. So I do the Feynman parameterizations, and then just to arrange my denominator, and then according to my using unshared conditions and according to the translation invariance, that means L bar I can always go to L bar plus something, some momentum, right? So then it goes to very simple integral, and actually this one is very simple because this one is not depends on x, so I like to integrate my x over, so I goes to this one, and then I can integration. Then I can decompose my loop momentum into the time component, 0 component, and the d-1 space component. We use, of course, because we are in microspace, so you need the matrix is plus to the 0 component and minus to the space component, and write explicitly out. And then I do the Wick rotations and perform the Cepheric coordinate, right? Then I come back to this. It's a Cepheric coordinate of the solid angle and that's a radial integration. And then integration out over the solid angle, it gives these, right? In general, d dimensions. And then we see this. We come back to this one. So this one very interesting because this one, if you calculate d equal to, you will see that if you set d equal to 4, then it's both divergent in the 0, the L bar equals to 0 and plus infinity. Okay, they're both divergent. So that's why we need to introduce d here, not directly to use the d equal to 4. So I decompose it into these integrals into 0, 1, and 1 infinity. Okay, and this is both. I mean, if you d equal to, you see that if L bar magnitude goes to 0, right? So this one, right, the red one goes to 0. It's infinity when the real part of the dimension is smaller than 4. Okay, so I mean, you can imagine this, if it's just a Leo, then if you calculate d equal to 3 or d equal to 4, then it might be gives you infinity. So if you get infinity, of course you don't get anything because mathematics tells us that we cannot get anything from the infinity, right? So if you, for this integral, if you go to L bar equals infinity, then the integral is also divergent when the real part of d is larger than 4. Okay, so actually, so that means d equal 4 is the most problem case because d equal 4 both are infinite divergent, right? Most are gives infinite numbers. So the regularization, dimensional regularization tells us that we set d equal to 4 minus 2 epsilon. However, we take the limit of epsilon is different for the infrared region and the ultraviolet region, right? In order to make the integral is finite. So from the infrared region, we need to take from the go to the 0 minus. That means to the Leo x. If you use the Leo, from the minus value goes to a 0 from the negative Leo axis, right? And ultraviolet is from the positive value to the to 0, right? Positive Leo axis to 0, for example, right? And in that case, we can get both the finite values. So wait, I didn't. Yeah. So this is I calculate that. So I do this way, right? I neglect all of the IR high dimension power terms, or the IR part of the UV power terms. In the case, I need set to 0. So then I come back to these terms, okay, these two terms. So you see that they're both divergent. And if you set, usually people say UV is equal to IR, epsilon UV is equal to IR, because they go to both zeros, so it's just a 0, right? But here I would explicitly write out that you have both ultraviolet divergent and infrared divergent, okay? But come from different regions of your integration. So I let you do the exercise of the remaining of the integrals. You can do really by hands. I think you don't need the computers. And so then for the amplitude, so I calculated right now the loop integrals. I need to get my amplitude squared, right? Because my cross section. So I don't do the one loop squared at negative linear calculation because one loop squared gives you alpha s squared compared to my Born squared, right, amplitude. So I do is one loop times Born conjugate, complex conjugate, right? And of course you need a complex conjugate term again, so that will give the 2 times of real part. And this gives me, if you calculate all the integrals that to perform the similar Dirac algebras, you will see that this is what I get, okay? So I factor out my Born squared. And this is UV poles and infrared poles. I actually double infrared poles and 1 infrared poles and final term. I neglect all the infrared pole, the epsilon squared, epsilon terms in linear and square in power. Okay? So, of course, I have, especially I have the divergence is UV, 2 over 3 epsilon UV. And this is divergence need normalization. We have no other ways to get rid of it. So you need a normalization. And the normalization counter terms, or normalization 1 is also similarly is UV times Born squared. This gives me 2 over 3 epsilon, but minus, okay? So this cancels the UV divergence. However, in my normalization, I also infer the divergence. Okay, it's not UV linearization. It's not only the UV divergence because I'm working in the unshared scheme, and this actually I get rid of the loops of the external legs, and this will give me 1 over epsilon IR. This is just a trick. Okay, you just avoid some simplification. So this one indeed also gave me IR divergence as well. Okay, so this is a UV and the linearization comes from my quark legs, right? Wave functions of my quark legs, 2 quark legs. I need to do linearization. So that's a cancels, UV divergence cancels, and some of them, then I just get my virtual matrix element. Okay, I arrived at my virtual matrix element. So this is I define as V. Okay. So then a Leo. Okay, I need a Leo as well. Because I still remaining some. Still remaining some divergence of the IR. I also need a Leo. So write down your real amplitude according to Feynman rules. You have 2 real amplitude diagrams right now. And squaring them, summing over colors, spin, same thing, to same techniques, and you go to amplitude squared. You go to the factor outside born. You go to 1 over S. The propagator of S24 and propagator S34 and something of D dimensions. Okay, I keep the D dimensions. So 24 is just the invariance of this U quark. So P2 plus P4. And P3, P4 is S34. Okay, and quark and gluon. The point is we need to do the phase space integration. Okay, and the phase space integration is not like previously in the Born. I actually also write D dimensions. The reason is phase space integration in the Leo is also divergent. So I needed to do the D dimension regularization for the phase space integration as well. So I write that in general to write 3-body phase space integration times are my Leo matrix element squared, right? And in D dimensions, okay? And oh, this is flux. Okay, so this is flux. So this is, don't worry. I mean, the flux differently in the cross section and the width. The conventional way is I try to dimensionless my quantity, integration quantity. So I introduce y is equal to 3/4 over mc squared, and 1 minus y, 1 minus z is s 2/4 mz squared. Okay, then. The thing is I need to take care of, I need to notice that in D dimensions of 2-body phase space, I can write these solid angle. So you see that my 2-body phase space integrations is just a solid angle, right? But my Born amplitude is not dependent on any solid angle squared, right? So you can integrate directly. And 3-body phase space, actually you can factorize. I think I wouldn't derive the here, but you can do yourself after the class to see that whether these derivations correct. So you see that you can do the D dimensions and integrate except the solid angles. You also have the dz and the dy integrations. Okay, and there's a minus epsilon is very important to regulate divergence. And this is I can completely factorize out my 2-body phase space. Times some factors, epsilon dependent factors, and dz dy integrations. Okay. So come back to my I need to my 3-body phase space integration. Especially I need to integrate dz dy to my amplitude squared, right? So amplitude squared right now is a y, 1 minus z, 1 minus y. It's important is these the denominators because integration them. If you d go to 4, then they are divergent. Okay, when you y goes to 1 minus z, that means these propagators are unshared. So remember that. Oops, no. Wait, yeah. Remember that if y goes to 1 minus z is 0, so S24 is 0, right? So S24 is 0 means this is unshared, right? This is unshared. So this gives me that if y goes to 1 minus z, S24 is 0. If you d goes to this smaller than 4, then it will give divergent. You just integrate these, okay? Yeah, integrate dy, okay? Similarly, if y goes to 0, that means S34 is 0. It's unshared. Okay? And how these can achieve this is can both sides, right? If your ground momentum is much, much smaller, goes to 0, that means z goes to 0, this will arrive the S24 is equal to 0. Okay? So that means y goes to 1 minus z. And this is if ground is soft enough, that means soft, okay? Momentum is small compared to others. So it's a soft singularity. This is my soft singularity. And also if PG and PQ is value running in the same directions, they are collinear, then this is also S24 is also 0. So it's a collinear singularity. Same thing to here. Huh? Just ground goes to anti-quark and ground goes soft. So then I do perform my Leo gamma term to the 3-body phase space. Then I just integrate, factorize out my 2-body phase space and Born, and then integrate out my dz and dy. Then I get also inferred divergence. So here, Leo, I only have the inferred divergence. I do not have ultraviolet divergence. Okay? And the good thing is you will see that all your 1 over epsilon squared and 1 over epsilon just exactly identical but minus sign with your virtual 1, okay? If you check previously. Oops. No, it's too fast. Yeah. So if you sum this, so if you're looking at the double pole is 1 minus 4 over 3 epsilon squared, and the double pole of the Leo is 4 over 3 epsilon I squared, right? So just cancels. So that means all the poles cancels unless you include all both the real and your virtual, okay? So some real and virtual gives you the virtual, of course, as defined here, the gamma virtual. Some of them just gives you alpha s over pi and epsilon dependent prefactors and Born. Okay. So, oops. Okay. So in general, of course, this example already shows you that real, if you include the real and virtuals, you get all the poles cancels. Of course, virtual you need a normalization to cancel the UV poles. But in general, all IR poles cancels is by, there's proof of the, in general in quantum field theory, is all the quantum mechanics is by Knight, Lee, and Naumburg is KON theory, well-known KON theory, right? For any inferred safe quantities, in principle, you sum of all the real and virtual, you will get inferred pole cancels. So this is what, I mean, if you sum them, integrate out, it's just the Born times alpha s over pi. So this is, I get a famous result. Huh? So I think you can reproduce your by hand to see that if you have no experience of negative linear calculation before, it's very interesting that you can reproduce alpha s over pi. It's very famous result, very simple enough and by hand. Okay? So if you get, and probably you will get a bit proud of your ability to calculate negative linear by hand. So we finally get a well-known result. So exercise for you is filling all the gaps because I do not show all the step by step. So many integrals I do not calculations. I just calculate one, and there's many derivations I do not show you intermediate steps. So filling all the gaps and to get the result alpha s of pi. Okay. So the k factor means the negative leading order over leading order 1. So its k factor is 1 plus alpha s of pi. But in general, of course, you see that if you calculate this one by hand, you will see that negative linear calculation actually is not very easy and it's very tedious usually. I mean, I want to repeat to doing my calculations do these kind of techniques in the iterative ways. So that's why I think you are here to trying to use in the computer code that is medical 5 and so on, right? So then I think, how much time do you still have left over? 20 minutes. 25 minutes, okay. So I think I would a bit using the, to go to the next two lectures about the generic of the next two leading order. In general, of course, there's a modern techniques developed, and you can use, I mean, you can understand what kind of technology behind on the market and also especially on the meta graph. So we see already that's previously we see a decay next to leading order, but similar as a cross-section is next to leading cross-section. We can see that is the Born amplitude squared times the n-body final state phase space integration, virtual and n-body phase space integration. One loop, of course, one loop times times Born. Then real squared matrix element squared, but is n plus 1 phase space ones, phase space integration. So this is alpha SB. This is alpha SB plus 1 and alpha SB plus 2. B plus 1, sorry. B plus 1 as well. Sorry. So this one we call Born cross-section. This is called the virtual corrections and the Leo correction. This terminology I already used in previously, right? And then remember that from previous example, we see that the Born is finite, phase space integration. Virtual is divergent, but for the loop integration, not phase space integration. And real is divergent, but for the one phase space integration, one body phase space integration. Okay, and only some of them you get a cancel of the inferred divergence. Of course, for the virtual you need the randomization. So first we go to the virtual. So virtual means loop plus UV randomization. Okay. What the meta graph do is basically meta graph do not use any external loop diagram generations, unlike other programs, okay? Like Shepa or something, they're using external one loop providers. Meta graph is a single framework standard learn to provide all pieces of negative linear calculations, except shower, of course. But I mean, at matrix element level, to provide all these kind of things, and also include matching. So meta graph will generate loop amplitude and loop diagram, but based on the tree-level diagram generation architectures. The basic idea is if you want to looking at the E plus E or whatever, I mean UU bar to ZZ go to the QQ bar and these diagrams, okay? How do you do? E plus E minus to UU bar? How do you do? I just cut one loop legs, then I will come back to my tree amplitude. So I can use a meta graph of a generation tree amplitude to construct my loop amplitude. However, there's of course the legs of cut loop legs. This I think 6, 5, and these 3 and 4. I think the numbers is random array, but I mean there's cut loops. If you cut in, then go to 2 external legs of the UU bar. They are treated differently with true external legs, right? So similar thing for here. So this is basic idea behind how the loop diagrams or loop amplitude generated in meta graph. Then, of course, if you generate diagram, you need to calculate loop integrals, right? So this is in general, you can consider the loop integrals of n points, the loop integral of this external momentum. And of course, you have a numerator as you showed previously. It's not 1, right? In the decay case, if it's not 1. And the numerator, denominator of the propagators, each propagators, you see write in general way, always you can write in this way. And write the integral is the in-dimensional regularization. It's in D. It's not in full because we need to regulate the singularity. So in general, that you will see, similar as what we have a previous example, you will see that any one loop amplitude can be expressed into some basis. The basis must up to the box in one loop case. So the box integral, but the scalar integral. So you see that the numerator is 1 right now, okay? But there's 4 propagators, 3 propagators, 2 propagators, and 1 loop propagators, plus some rational terms. And of course, I neglected the epsilon high terms. So A, B, C, D, they are coefficient, but they are not dependent on the loop momentum anymore, but only depend on external parameters and external momentum. Okay? And rational term is just a rational functions of the external momentum and external parameters. Okay? So reduction of the loop to this scale, this is a general case. You can prove that. And this one, how this can be achieved to reduce to get these coefficients basically there are two ways on the market. One is the tensor integral reduction. Actually, we have already showed, and that is one of the tensor integral reduction. It's Pazzolino-Welterman method. And also, you can reduction at the integrand level. It's a bit new. So Pazzolino-Welterman, we have already shown in previous example. In general, idea is you want to get your tensor integral NL to be convergent. So how do you do this? How do you do this? You can see that you just write all your tensor integrals, L nu, right, or more tensor integrals. And this is being implemented in several public code. And you will see that how do you do is just times, because you can write, according to Lorentz structure, you can write it is the external momentum enters into your loop integrals and also the matrix ways, right? So then do the conjugate with the external momentum and the matrix. Here is just a conjugate with external momentums P nu and Q nu. And then you get the coefficient. So yeah, this is we write. Previously I write B1 and B2. Here is write C1 and C2. Okay, P nu and Q nu, and then construct these to L times P integral. You multiply to P nu times L nu, and then write left-handed multiply left-handed multiply right-handed, and then you get to this matrix C1 and C2. And this one you know how to simplify further, right? With reduced denominators. So this is an example, same thing. Similar example as we showed before. So to make your integral, numerator integral just be 1, okay? Numerator of the integral. So then, so this R2 is not the R2 I will introduce before, but later. But this R2 is here, right? So just 2Q times L. 2Q times L, you can do the same thing. And then we can solve. If we know the R1, R2, we just can solve what is C1, C2. Just reverse the matrix. So this matrix is a grammar matrix. So then we get in terms of the scalar function C1, C2, or in terms function in scalar functions, or the tensor integrals in the scalar functions as well. My basis. So another thing is more recent. It's not 80s. It's proposed in 2006 by OPP. It's an integrand reduction. So the basic way idea is not to perform these decompositions or to get to confusions at integral level. Instead, I just perform the numerator into my denominator to perform these, get the confusion directly at the integrand level without integration. Okay. Of course, there's some complex because it's just NL is just not equal to D function times times some denominators, right? Because you have some external ones, but they are integrated to be 0. This does not appear after integration, but they will appear in your construction, your integrand, right? So they are called tutor ones. There are many tutor ones called spurious terms. Okay, so how 10?
Actually, there's enough time, but if you want to stop at some time.
There's enough time?
Yeah.
Okay, then I quickly, maybe I just finish the virtual part.
Yeah, you can finish it, stop at some time.
Okay, okay. So I just finished virtual part. Then I go to Leo in the next lecture. So the function form of this spurious term is known. That's a good thing. And it depends on the rank of the integral number of propagators in loops. This is a paper in 2004, has been proved. And one example is box confusion. So D tutor is just the D tutor, of course, integrand level. It's not It's not this d is independent of loop momentum, but d theta depend on the loop momentum. Okay, so d theta is dependent on loop momentum. It can be written as coefficients d theta times Levi-Civita terms, construct of the external momentum and loop momentum. Okay, and this one is actually, if you integrate these, it's going to be 0. Okay, because if for box diagrams at maxima you have 3 independent momentum enters into your propagators. So if you construct it, you will see that you have no false independent parameters after integrating the momentum. It's going to be always 0. So that's, I mean, that's the basic idea. So that's how can I calculate the d function, d and d theta. So the way of I know the d0 functions is I just calculate L, but I choose clever L because these linear equations is still very complicated, right? Oops. These linear equations still very complicated. So you need to choose some clever way of loop momentum. Right now, you can choose loop momentum as a complex value, not the real loop momentum. You can choose some complex value to make sure that your L plus is exactly equal to 1, this one. What does it mean? This means only D0, DI0, DI1, DI2, DI3 are non-zero. All the others are 0. Okay? All the others means this term must be 0 because you must enter, just exclude 3 of them, right? So you must enter, I mean, you just must enter that is non-zero terms comes into, right? So all the other terms are 0. Then NL is just equal to these, the box one, right? Oops. So NL equals box 1. Let's drop all the remaining terms. And then we get D0, 1, 2 is just, you just solve these two. This equation is very simple, right? So just solve these equations, right? And so that means you need to choose a clever loop momentum to calculate the coefficients of D0, D and D theta. So the general idea is same, right? So first to solve the, opposite way I'm talking about. To solve the OPP reduction, you need to choose that only the 4 propagator are 0, other propagator non-zero, right? Then, I mean, for triangles, it must be 1. I mean, because you just exclude 3, so it must be 1 enters into 0, enters into. So all the others are 0. Then to solve these equations and get to D. Of course, the loop momentum is complex to satisfy these equations. If you have the D and the D theta, then you can go further. You can subtract NL, subtract this one, go to next one. So this one is this one you know. Then you solve this to ask for 3 propagators to be 0, right? Then both should be non-zero or the remaining 0. So you can solve, you know this, so you can solve the C functions as well, right? To go further for the B coefficients, you can go to the further way, and for the 1-point function to the further. And this one is just spurious, so you don't care. Pure spurious, so integrating is 0. So after integrating is 0. So the integrand level is not 0, but after integration is 0. Right? So you get it. So all these previous were actually it's a bit naive because we haven't considered the d-dimensional quantities. So d-dimensional complex wave happens. Actually, the loop moment loop and the numerator in your loops is not a function of L. It's 4-dimensional quantities, and it would be the d-dimensional loop momentum dependent and epsilon dependent as well. Okay. And your propagator is a d-dimensional as well because the loop momentum enters is also d-dimensional. So in numerical calculation, it's very inconvenient to keep the L bar is d-dimensional, as I think Benjamin also mentioned once. So the convenient way is to performing the decompositions of the d quantities, all the d quantities, into four-dimensional quantities and minus 2 epsilon dimension quantities. So that means Lorentz index, you keep 0, 1, 2, 3, and the remaining to 3, 2 minus epsilon is minus 2 epsilon d dimensional space. But this is abstract space, okay? This is not the physical space, and 4D is the space-time of physical space-time. So it decomposes these two things, okay? So L nu, that means if nu is to minus 2D dimensional space, L nu is 0, okay? L tilde nu is 0 when nu is the physical 4D space-time, okay? Then my numerator can be decomposed into the only the four-dimensional loop momentum dependent, and there's no epsilon dependent anymore. And the remaining part, you just n tilde just subtraction these two, okay? And this one very convenient for the numerical calculation, numerical implementations. And this one is lucky because this one actually gives the epsilon term. It just gives the rational terms. And this is one has been supplemented with special rational term R2, okay? So the R2 terms, we needed to calculate. I mean, we know that NL dependent term, oops, it's very sensitive. Yeah. So NL terms, we already know you can do the integrand level decomposition as we already shown. The only task is to calculate n tilde term, right? So n tilde term you can define this way, R2, right? And this one is the good thing is to prove that it is only UV related. So you can literally, that means you can literally write into the UV counterterms, the renormalization counterterms, write into Feynman rules, okay? Write into Feynman rules. So this is one example. If you calculate the wrong self-energy with TT bar, you write the loop momentum in the general D-dimensional is this way, okay? Then you can perform some Dirac algebra with taking out trace, and remember that epsilon nu are external ones, right? So then you can split the 4-dimension and epsilon one, 2 minus epsilon dependent one. So n tilde is this. Okay, very simple. So that, remember that this is only, right now there's no epsilon dependent explicitly, but n tilde square dependent. Okay, this is a extend stop. Okay. So okay, I will continue with the R2 in the next lecture. So okay, thanks.